Good evening, everyone. Today, we have a wonderful speaker, Dr. Anshul Sindhwani, is a distinguished lead engineering geologist with over about 10 years of expertise in geological, geotechnical, and tunneling works for urban metro infrastructure projects. With PhD in tunneling from IIT Dhanbad, his groundbreaking research focuses on optimizing tunnel boring machine performance in varied ground conditions using advanced techniques such as artificial neural network and multivariate regression analysis. Dr. Sindhwani has played a pivotal role in major metro projects across India, including Delhi, Mumbai, where he has led geotechnical investigation, instrumentation, and the design and execution of complex tunneling operations. His hands-on experience with the TBM and NATM tunneling, coupled with his contribution to risk mitigation in challenging urban environments, make him sought-after expert in the field. Dr. Sinvani has published extensively in leading journals and conferences and is a recipient of the prestigious award like PJ Rao Wayarful Award for the best paper on geotechnical professional practice. He is also a member of professional bodies such as Indian Society of Engineering Geology and Tunneling Association of India. Over to you, Anshul sir. All the best for the webinar.
Yeah, thank you. Thank you, Aditya. Good evening, everyone. Thank you for the introduction, Aditya. Also, thank you to the TAIym team for the invitation and giving this opportunity to present. Also, I'm happy to see the success which TAIym has made so far, specifically in this webinar series, which was, I remember, initiated during the COVID era when I was fortunate to be part of that committee during the year 2021. Yeah, so let's start. I'll just share the presentation. And once the presentation is done, I'll be happy to take questions if you have any. Aditya, can you please confirm if the presentation is visible?
Yes, sir, it is visible.
Yeah, just hold on. I'll just switch off my camera. Yeah, so I'll be discussing on ground characterization and TBM performance evaluation in challenging ground conditions. I'm hopeful I'll be sharing some valuable insights with all the attendees today. So I'll just start now. Yeah, so some of the summary which I'll be covering today, introduction of the particular case which I am speaking about, geology of that area, geophysical investigations, ground improvement. We had made some key observations before TBM excavation and during TBM excavation. So since the topic is focused on the challenging ground conditions, so what exactly is the effect of these difficult ground conditions we had on the TBM advance rates? Then I'll just conclude. Yeah. So, use of TBMs in urban and hydro projects have gained increased popularity in recent years. As we all know, it offers comparatively fast, safe, and high-speed tunneling. However, we all know, I mean, it's always the culprit that the lack of extensive investigation leads to cost and time overrun of these projects. So, the presented study will be an ideal example of how the integration of different sort of investigations helps in reducing the ground uncertainties. So this is one of the project of Mumbai where I've been involved as the engineering geologist. So the study location is exactly, if you can see, this was the Arabian Sea. This is in South Mumbai, and this particular location is sitting next to the sea. We call it as Machimar Nagar location. So this is particular location I'll be specifically speaking on with regard to the today's topic. If you can see a closer view of that particular location, you can clearly see the tunnel alignment was exactly sitting next to the sea shore. So obviously, as a layman, also we expect some sort of difficult ground we try to anticipate because of looking at the scenario which is here. So understanding the ground in a detailed manner is very important in this particular case, which we had got a feeling as a geological engineer. So this is just to have a more view. This was the view from standing on the top of the tunnel alignment, whereas this is from the sea side, if you can see. So this is the location where our TBM tunnel was supposed to drive below this particular road. So we can see there are high and low tide variations are also happening along the seashore. So if I just talk brief about the regional geology, so many of you might be aware of the fact that Mumbai was actually consisted of seven different islands if we go back to the geological time scale. And in fact, this Mumbai High Court, if any of you might have seen, was supposed to be the end of that specific Mumbai coast. However, during the course of time, what we can see clearly is this is the present situation. So if I just even backtrace this particular location along these three images, we can clearly see this was a part of sea earlier, and it is like a reclaimed land. So where this tunneling was proposed. So getting to know more about the ground is not just a requirement, but a necessity to understand what exactly the ground lies below. So if I just brief on the investigation layout, what we can see at the first, this orange color, what we can see here is just the one borehole which has been provided at the stage when we have been awarded the project. And then when we started, we did only two exploratory boreholes. But by the time we realized these two were not enough, only not because of the data what we have encountered, but also of the fact that we need to see what exactly is lying in the seaside. So these two additional boreholes also we had done. In addition, we have also gone for the geophysical investigations. We can clearly see these two lines, which I'll be speaking how exactly and why exactly these line, I mean these investigations in terms of geophysical also proposed during that course of time. Yeah. So if I'll just brief on again, I'll be talking about these two boreholes results, what we have got. So what we can see here, we had anticipated a filled up material and clay sand, silty sand of 7 meter deep. And then we had a weathered basalt layer below. And then there is a bedrock basalt in one of the borehole. Whereas in other borehole, you can clearly see there is a high degree of fracturation. And in fact, when we did packer permeability test in this particular zone, high water loss was also recorded, which indicates that the joints are open and fractured. I mean, degree of fracturation was obviously visible in this particular case. So these two indications have led us to conduct more study on the seaside. But when we moved on to the seaside, you can clearly see the boreholes we investigated on the roadside. But we found there is no problem as such what we were anticipating towards the sea. But if we go back to the layout again, in one of the borehole, it is indicating there is a fractured zone. But when we are moving towards the sea, it is having a good hard rock sitting below. So if we just conclude these two particular thing, you can clearly see the filled up material is rather going down. However, the degree of fracturation is only limited to this particular borehole. Other boreholes are indicating still a good rock. So the result of these pre-construction boreholes and additional probe holes revealed that the degree of fracturation is not continuous towards the seaside, which is like a perpendicular direction to the tunnel alignment. However, this continuity of fractured strata along the tunnel alignment is not established fully. So with the boreholes. So then we decided to move on to the geophysical investigations along this alignment to delineate the anomaly zones. So if I'll just go back to the layout, these two lines we had proposed in the form of both electrical resistivity as well as seismic reflection to have a detailed understanding and to integrate this data with the borehole investigation. So electrical resistivity did indicated low resistive layer. If we see the 3D section on one side, which is toward the sea side, you can clearly see a domination of a bedrock good having high resistivity. Whereas on the other side, which is rather away from the seaside, is having low resistive zones. Even if we see in this cross section, it clearly depicts a low resistive zone on one side, whereas on the other side, which in fact related well with our investigation which we carried on the seaside, and it revealed that the ground is definitely good when we are moving towards the seaside. Even when we go to the seismic reflection results, it clearly indicates there is a dipping of low velocity layer up to the tunnel depth in one of the lines which we had executed. So then what we did is we plotted the exact tunnel zones in this geophysical investigation results so as to ascertain exactly at what particular point this is happening. So in a seaside, we can clearly see there are high resistive zones, there is no problem. Whereas on other side, there are low resistive zones sitting. Even in the seismic velocity, like I've said, you can clearly see there is a a low velocity zone which is encountered here. So this with this data, we had got a confidence that the ground is not as bad as what we are expecting, but at the same time, this fracturation of continuity will be there, but it will be localized, maybe of 10 meter, 20 meter, 30 meter, but then it is not all along the sea, which we are anticipated at the first instance. So this certainly helped us to understand that the ground, what lies and what we are expecting during the TBM drive. But certainly after seeing this, we had to uh, go for the ground improvement as well. But there was a limitation when we are doing the grouting, because if you can see the zone which I'm indicating here through pointer, this was the zone where the slums were located. So in this particular zone, we could not able to do anything. Even on this side, it is a high traffic volume road running towards the Kulaba side. So even on the road, we could not able to do anything. This was a slums location where practically nothing can be done. So we only did the grouting at the zone where it was feasible, and we anticipated certain degree of fracturation in three lines. So line one, if you see, it was going up to 23-meter depth, which is almost 2 meter below the tunnel invert. Then there is a second line, we call it as a primary, secondary, and tertiary lines we created. Second line was also, which is secondary, which is also going up to the tunnel invert. And the third line was specifically made only for the filled up layer. Because if many of you might be aware of the fact that basaltic terrain have got subvertical joints, so we always had the possibility of the seawater seeping through this filled up layer through the vertical subvertical joints onto the tunnel alignment. So we did the grouting as a tertiary row only for the filled up layer, which is 7 to 8 meter deep. So this was limited only to this particular zone, but with the experience, I mean, this is just some photographs depicting the work we carried. So you can clearly see this is on the seaside, we did some improvement. This is just to give you a view of low tide and high tide. If you can clearly see on the bottom side, this is low tide time where we could able to execute in a better manner in comparison to the one which is on a high tide region where it was not easily executable. So moving forward, we had the investigations in place to ascertain the challenging ground we were thinking of. Then we moved on to the ground improvement. And now, just to sum up, there were some key observations what we made during before TBM excavation is this fracturation has been observed only in borehole, like I have discussed, and water loss consistently observed in the same borehole during in situ testing. Now, during drilling of holes for grouting, pressurized muddy water was coming out of holes like a fountain. I'll just show the video to understand more on this aspect. Just trying, yeah. Hope it is visible now. Yeah. So when we started executing the ground improvement, you can clearly see after the drilling is done, we were about to start the grouting. You can clearly see how the water is coming out. So it really indicates the fact that this is a reclaimed zone. And since we have punctured this reclaimed ground, this pressurized water which was there in place in the ground, it is coming out with some certain pressure. However, we moved ahead with the grouting, but then we again, it has given an indication that the ground, what we are, again, there might be some challenges which we are not able to fully uh, like lineate the fact that where exactly it is there, but it must be there in patches is what our understanding is. So what we did is big watering pumps and grouting provision. We also made it ready from inside the TBM so as to assure that if, let's say, any sort of situation comes in during TBM excavation, we'll be ready enough to allow for high dewatering, as well as we also be ready for pre-excavation grouting from the TBM. Now, during the actual execution, since we are already aware of the fact that this is going to be running near the sea, so we know the exactly changes where exactly it has to come. So there are three different zones. I'll just choose the pointer. Yeah. So the zone one was grade 2 basalt, weathering grade 2 we call. And then there is a moderately weathered zone, which is a grade 3. And then there is a completely to highly weathered basalt, which is what we have been seeing in different pockets during our different course of investigation. Even if you see the right hand side, during the regular phase inspections, at once we only encountered these weathering along the joints. This weathering has increased slightly. Now here you can see it has increased more than 50%, whereas here if you can see it is almost as good as 80 to 100% weathering. So like I've said, zone 1 is a unweathered to slightly weathered basalt with moderate water ingress. Zone 2, where we had anticipated high water ingress, and zone 3, where it has led to many challenges, which I'll be discussing subsequently. Yeah. So this is in terms of TBM advance rates, what we have actually uh, achieved during the course, exactly near to the sea. So this is again to depict we were doing two things at a time. One is the phase inspection, where we are physically seeing the ground, and another is rock chips evaluation also we were doing. So you can clearly see how this degree of weathering is increasing as we are moving in different zones. So the zone one, which is a good, or rather I should say unweathered or slightly weathered basalt, achieved rates of 40 to 50 meter per week. In zone two, it has even increased to 54 meter. This is because of the fact that it is a moderately weathered. So ideally, the UCS becomes low in comparison to zone one. Even the RQD becomes low. So it is easier to achieve more progress. However, when we move towards zone three, you can clearly see a 50% reduction in the advance rates of 20 to 25 meter per week. And beyond zone three, again, if you can see, slowly we have moved towards the same zone what we were getting in the zone one. So this fourth zone is indicating this particular zone where you can clearly see again the unweathered basalt has been encountered. So if I talk about the zone one, it was having compressive strength of more than 60 MPa. RQD was in a range of 70 to 100%, and we were classifying it as class 2 rock. Whereas in zone 2, where we achieved 54 meter per week, the compressive strength has reduced, like I said. RQD was again 40 to 70%, and RMR we classified as class 3. Now, zone 2, like I said, achieved marginally higher advance rates owing to low compressive strength as compared to zone 1 and moderate degree of fracturing as well, which actually favors the chipping process. Yeah. So moving on to the zone 3, you can clearly see there is a muddy water coming out of the conveyor, and you can on the right hand side you can clearly see it is like a slush which is coming out. So 80 to 90% was mainly the silt material, and then balance 10 to 20% was the weathered rock chips which we had encountered. So this was more about what exactly we had encountered and what we thought of, and I mean what we anticipated before TBM excavation. Now I'll be talking about the evaluation part in terms of the TBM performance, since the TBM performance is directly linked, and we know how to operate in these particular situations. If we are facing a challenging ground conditions, doesn't mean nothing can be done. Certain amount of uh, challenges can be reduced by optimizing the TBM operational parameters, which you will see it here. So I'll be speaking on 6 different parameters. First 3 parameters are more of related to the operations part, which is like an what is in our control, and then there is a performance parameters, which is more related to the penetration rates. So if we can see in zone one, which is this particular zone, the thrust force was varied between 10,000 to 14,000. Since it is a unweathered or slightly weathered rock mass, so basically higher thrust force are required. Whereas in zone 2, if we see, the thrust force has reduced below this green line and it is indicating a range of 8,000 to 10,000. So now this reduction is witnessed, like I said, because of the moderate degree of fracturation and low compressive strength, it has basically eased the chipping process. So the thrust requirements has been reduced. Whereas in zone 3, you can clearly see there is a shoot up of these thrust forces. Now these thrust forces, ideally, if we go by the rock strength, it should reduce. But in this particular case, since we had to reduce the confine this convergence above ground, we had to reduce the surface settlements. There has to be extra muck which has to be kept in the chamber. So it is more of a excavation chamber which has increased the thrust. So we were going slow and at the same time keeping the muck within the chamber so that we can reduce the surface settlement. So this is not by grace of anything. It is more of a operational strategy where we are trying to reduce the challenges what we have been facing. So this clearly depicts this fact that in this particular zone, these thrust force have been increased. Now beyond zone 3, if we see again, it has dropped back and following a range of this green line, which was there in zone 1. If I move to the other parameter, which is torque, in zone 1, if we can see, this is more of following a range of 1500 to 3000. It indicates there is a smooth cutting of rock mass on face is happening. Whereas in zone 2, again, like we know, because of the moderate degree of fracturation and reduction of thrust forces, this torque has also reduced a bit. Again, whereas in zone 3, if we clearly see there is a high scattering. Now, this scattering is happening because of, again, a very technical fact that when you have a fractured rock on the face of TBM, there are always undulations. So when you have undulations, the cutters get more impact loading when it is being in touch with the rock mass, whereas on the other side there is no rock mass because of this degree of fracturation. So it clearly depicts that this zone 3 indicating a higher and lower values, which is creating a scattering pattern. So this is again revealing the fact that the ground remains fractured in zone 3. Now, if we go to the cutter head rotation speed, which is nothing but how many times the cutter head has been revolved in a minute. So for zone 1, if we clearly see, we have followed a range of 2 to 3 revolutions per minute. This is bare minimum required because you have a hard rock in your ahead of the TBM phase. So you need the revolutions to be on a higher side so as to facilitate optimized penetration rate. Whereas in zone 2, since we are getting a low thrust force and the speeds are also increased, so we can clearly see the increase in the RPM, which has facilitated higher advance rates. In zone 3, if we go back, there is a range bound we had followed. If we see on the first end, it has been from 1.5 to 2 only, and slowly it has increased and it has followed a pattern of this 1.25 to 3 only. If I'll just sum up in this particular table, you can see all 3 parameters at once: thrust force, torque, and operational RPM, which is indicating the TBM operational parameters. Now, reduction in RPM is also to limit the disturbance to this highly fractured rock, because the more RPM if we provide, there will be more degree of fracturation at the face, which will lead to more settlements and more shield confinement as well. So I forgot to tell you one thing. This thrust forces has not only increased because of the extra muck we are keeping in the chamber, but also because of the shield confinement. So when we have a fractured zone, our shield has passed on from that fractured zone. Now, because of this highly fractured, this ground tends to settle in. So there is a higher friction forces in the shield which is happening, which is creating more thrust force. Now moving on to the performance parameters. The first parameter is penetration per revolution. So if we see in zone 1, it has clearly followed a range of 8 to 16 to 20 mm per revolution. Whereas in zone 2, it has again followed a same range, but then it is shooting up a bit. But then if I conclude it has mostly followed a range of this 10 to 20 mm per revolution. Whereas in zone 3, since we are going slow, we are cutting the rock flow. You can clearly see there is a dip below 10 mm. Average, if you see, it is coming out to be 6 to 8 mm only. Now, this again indicates the fact that we were, by our own will, we are going slow so as to assure we are limiting the surface settlements. At the same time, we are ensuring the less water ingress is happening. Now, if we move on to the penetration rate, now, penetration rate is nothing but almost same as what I talked about the penetration rate in a previous slide. The only difference is here we are talking about the penetration rate as mm per minute. So when you have a penetration per revolution, you just multiply with the cutter head rotation RPM. So let's say if you are getting a penetration per revolution as 10 mm, and your RPM is maintained as 2 mm. So just a multiplication of 10 into 2, it becomes 20 mm per minute. So if we see in zone 1, overall it has recorded a range of 20 to 40. In zone 2, if we see, it has shooted up, which is resulting in higher progress as what we have seen in the meter per week chart. And in zone 3, again, if we see, it has reduced below 20 mm per minute. Again, because of the fact, like I said, we are by will we are going slow. So now this particular zone, like I said, this has reduced for efficient control of muck removal as well as to ensure and minimizing the surface settlements as well as to ensure the water ingress which is happening. We have to control that. Moving on to the next parameter. So this is ROP, which is again, I mean, it is same as what I've talked about in the previous two slides, but it is in terms of meter per hour. So let's say you have a mined length of each segments and you just divide with the total time. So you get the meter per hour rate. So let's say generally the segment length varies from 1.2 to 1.5. So let's say you have completed the mining of 1.5 meter in 80 minutes. You just convert into meter per hour. So if we see in zone 1, we can clearly see it has followed a range of 1.5 to 2.2. Whereas in zone 2, it has increased from 2 to 2.8 zone. In zone 3, of up to 1 meter per hour. So if I conclude and sum up of all these three, I mean, to summarize all these three penetration parameters in different zones, in grade 1 and 2 basalt, the pre-revolution was in a range of 8 to 14, penetration rate 15 to 45, uh, and meter per hour, it is 1.5 to 2.2. Whereas in zone 2, which is grade 3 basalt, the penetration revolution is 15 to 30 mm per revolution. Penetration rate is 35 to 55, whereas ROP is 2 to 2.8 meter per hour. Now in zone 3, which is grade 4 and grade 5 basalt, the penetration revolution is limited to 6 to 12, penetration rate 10 to 20, and ROP is zero point 0.9 to 1.5. So overall, if we see how exactly this different zones had affected our TBM performance. So zone 1 has proved to be good for tunneling. We expect that in hard rock. So we achieved higher advance rates of up to 50 meter per week consistently. Whereas in zone 2, it led to high water ingress. But then since the rock is hard, doesn't giving any sort of a challenge, we managed well owing to high dewatering capacity. which we were prepared enough in advance. And then the advance rates are almost similar, maybe 5 to 10 meter. It's, comes into the same range. And zone 3, it has led to huge water ingress with slush and crushed rock mass, which caused a drastic reduction in the advance rates of up to 25 meter per week. So this fractured zone has led to significant increase in applied thrust force, like I said, due to shield confinement and also caused by collapsing ground above ground. For zone 2, a combination of high RBM and increased penetration resulted in ease of borability and a chipping process, whereas in zone 1, there was a reduction in feed evolution in comparison to zone 2 because of high UCS, unaltered joints, and low joint frequency. Now, ground conditions near to sea proved to be challenging. The continuous presence of water significantly altered these joints and rock properties. As we all know, when we talk about geological timescale in millions of years of these rock formation, it has been significantly altered. Now here, if we see, since it was close to sea, the degree of weathering was quite excessive in comparison to what the degree of weathering, if we see the rate, here it was more because of the presence of sea in vicinity. So slightly to moderately weathered basalt in zone 1 and 2 doesn't cause any reduction in the TBM performance and the advance rates, whereas highly to completely weathered basalt and this fractured basaltic mass caused a significant reduction in the TBM performance and advance rates. So with this, there are some key takeaways. First, like I have tried to explain in detail how exactly the borehole different stages, pre-tender, after award of tender, and even after first round of investigation, how we led to the second round of investigation. Then we decided to go for geophysical investigation. Now, when we integrated all these investigations, we really got to know that challenges are there, but then the level of challenges and the extent of it was not fully known, but then it had actually helped us to prepare ourselves to face those situations. And in fact, given us a way how to optimize the TBM parameters well in advance. Now, the results definitely we can see it highlights the effect of highly fractured rock mass causing a significant reduction in the TBM performance. So we, by the time we have realized the fact that what are the benefits of integrating the findings of different sort of investigations. So even with geophysical, when we are recommending, we always try to go for at least two different geophysical types because it sort of help us to correlate even within these two, and it gives, let's say, any sort of ambiguity, then we can go and relate with the borehole investigation. So even with geophysical, we always go try to recommend two types of different geophysical investigation, and then if we relate with the borehole investigation, it really gives you a better understanding of the ground. Then ground improvement selection was also important. In this particular case, our intention was only to consolidate the rock joints, which we found at open at many places in the borehole drilling when we were doing. So the ground improvement selection we had to do. It may have mitigated to the certain extent, but definitely it would have helped in a better manner. And then the last thing is key operational parameters needs to be adjusted to ensure passing through of TBMs. Like I said, these challenges are there when you are facing on the TBM. It is not that it will come on its own and you have to face. There are ways to optimize these parameters to ensure the TBMs can pass through in these difficult ground conditions. So if I just conclude, so one of the primary concerns in the urban tunnels which are planned near to sea is high water inflows. We have faced a lot of challenges in Chennai Metro, Mumbai Metro because of the vicinity of sea. And in fact, it sometimes floods the tunnel during the TBM excavation. Although since the ground is hard enough, it may not cause you surface settlements all the time, but definitely it floods the tunnel if we are not prepared. Now, risk mitigation is another very important aspect, which should be done through extensive investigations, and if required, some designed ground improvements must be done. However, the selection of a TBM is also a critical part. If the TBM's ability to handle such high water ingress is not there, then you are unable to do anything. Like I said, there are ways to optimize the operational parameters, but until and unless TBM doesn't have that capacity to maneuver in these sort of ground conditions, you'll not be able to do anything. So it is important to be considered. All these parameters should be considered when we are selecting the TBM, and adjusting these operational parameters are best suited for encountering such difficult ground conditions. And it is a key for successful passing through of these TBMs. So, in fact, I have published some of the papers related to this particular topic. You can see in this Indian Geotechnical Journal, I have published the same topic. And fortunately, I have also awarded for the same paper in one of the IGS conference, ground characterization and TBM performance evaluation in fractured basaltic terrain. So that's it from my end. Thank you very much. I would like to take questions if you have any.
Once again, thank you very much, Anshul sir, for such a wonderful presentation. And I think we should go ahead with the question and answer session. I think Mr. Manoj Kumar here have a question. Mr. Manoj, you can turn on your mic and camera if you want and ask the question.
Yes, Anshul, thank you for this great presentation. And I would like to ask something. How much water you observed during this mining, and what was the difference as expected during GIR, and what are the precaution measures taken to successfully this passing? So yeah, consolidation grouting is different, but if any additional like pre-grouting we have done for this during this passing this zone, so please.
Yeah. So, sir, like I said, in one of the boreholes where this first indication we recorded, this water loss was happening. So I think if I remember correctly, it was 200 liters per minute. Uh, in the borehole, I'm referring. Now, regarding the mitigation, like I said, wherever the feasibility was there on the surface, we planned this consolidation grouting, and our TBM was capable enough to ensure the grouting of the TBM if required. But then, fortunately, we could not get the chance to use it because we were able to manage the ground condition. Like I said, there were no high-rise buildings on the surface. If it might have been there, we would have gone for some extra grouting from the TBM. But you know the practicality and difficulty in executing the grouting from the TBM. So since we were able to manage the ingress and the difficult ground conditions with some reduced productivity, we had gone ahead with that. And later, once the segments got erected, we did the consolidation grouting again with some high pressures. I think I have answered the question. If I've missed anything, if you can just ask me.
Okay, and in addition, one more thing. After passing this zone, is there any settlement measured, or is there any difference if any instruments was installed at ground?
Yes, sir. We had installed MPBX, and piezometers were there because we had this low tide, high tide fluctuations. But then, like I said, this overall geology is not very weak, and at the same time, in the fractured zone, we could able to maintain the chamber pressure, and we were going slow. So it has worked in a way to limit these settlements. If I'm not wrong, I think not more than 8 of settlements we had recorded in that place.
Okay, thank you.
Thank you, sir.
I think we have another question from Ms. Lalita. What kind of test can be performed in marshy land to understand the ground behavior?
Lalita, actually, this particular case, if you see, it may look as a marshy land, but you are well aware of this Mumbai conditions. I mean, at Haji Ali, if you see Marine Drive, if you see I mean, basaltic rock mass is sitting at the sea level itself. So in this particular case, we were encountering the rock from the ground level itself. So there was no as such requirement. But ideally, see, even if a land is marshy, what I believe is we only have the capacity to understand the C5 and all the soil parameters which are required. There is no specific test recommendation I have seen, I think. I think I have answers your question.
Yes, sir. Uh, Another
I
question
think
from
there's
Rishi.
one more
Any
question.
special provisions for TBM segment gaskets?
No, no any special arrangements made, because ideally, I mean, it is already being a, a proven thing. So it takes care of the water ingress well in advance. Even during the design stage itself, the requirement, it's because of these shallow urban tunneling, this groundwater condition is present everywhere. So these are being taken care. There is no additional pressure because the grouting has been done behind the segments. There is no any specific or uniqueness in terms of gasket I have at least seen. I may not be an expert to comment on this particular topic. I can
Sir,
see
there
some
was
more questions in the
another
Q&A.
question as well from Mr. Sachin. Uh,
Yeah. Yeah, I've read the question. I have not included the TBM specifications, but since you have asked, I can just brief on a bit. This was a crossover dual mode TBM Robbins had deployed. So it has the capacity to work both in a rock mode as well as the EPB mode. So why we call it as dual mode is because they have I mean, the machine has dual kind of drive motors. So there is a EPB mode and there is a rock mode. So let's say when you're encountering such challenging conditions, you basically switch on to the EPB mode where you can handle certain water pressures. So this is one of the unique specification we had been using for these particular TBMs. And cutter head parameters, if I'll just brief on, it was a 10% opening ratio, 90 mm disc to disc spacing, almost, if I remember correctly, around 30 to, I mean, 35 plus 5 disc cutters. So this mostly dictates the cutter head configuration, if I'm correct.
yes, I hopefully this answers the queries of Mr. Sachin. Uh, we'll wait if we have another questions from audience.
I think there are other questions coming in. Yeah, I can see by Mr. Pankaj. I'll just read out. Please suggest what should be the TBM parameters while crossing the low cover zone or thrust zone where disking has been recorded in borehole along the tunnel alignment. See, the urban tunneling cover has much low than the low cover what you have been specifying here. 40 meter is more than enough when we compare to the urban tunnels where it is as low as 4 to 8 meter in many of the cases. But the point is there are no uh, specific range of any individual parameter of TBM when we talk about, because there are many limitations in this. We need to know the dia of TBM. Then within that dia, what exactly the mode it is operating, like a EPB, it is a slurry. So there is a no specific parameter specification is being given by any of the authorities till date. So as to ascertain, let's say this type of geology is there, you need to apply this. It is like a optimized learning. So ideally, I mean, there are autonomous TBMs in place right now in many countries, Singapore, Sydney. So what you do is you learn the ground conditions. You see what exactly the parameters of TBMs are recorded on a day-to-day basis. And then you see and decide that this particular parameter is working and this particular range is working well and giving us, see, at the end of the day, what you need is you should minimize the settlements. Your ground should not be more fractured. At the same time, you should get a decent progress. So these three things can be depicted well in any TBM operational and performance parameters. So you need to really stick on as a underground engineer, as a geologist, as a geotechnical engineer. What we need to see is not only the ground, but we need to relate it with the TBM recorded parameters. And then we need to see what exactly is the range coming out for different zones. So let's say from grade 1 to grade 5 of that particular project you are working in, you will get these parameters recorded. You need to analyze this, and then you can say, okay, this might be a best working case. So there is no direct calculation available where you can say this is the 40-meter zone. What should be the thrust zone? Because there are many TBM operational parameters itself dictates all these things.
Okay, sir. And how you manage groundwater behind the segments after the passing of groundwater bearing zone?
Like I said, we could not do the grouting from the TBM, but what we did is as soon as we had passed this location, so what has happened? It has actually created a passage. This water was still coming out from the rock, but it has created a passage above the segments and it was coming out from the space. So even though we were moved to a good basaltic zone, but then this water was still coming in. So what we did is, as soon as we passed this zone, we started grouting. So we used PU to block the water. Some epoxy grouts we used first, and then we used the cementatious grout to consolidate the ground. So that was done it at a later stage, but in an extensive manner, so as to assure that the seepage doesn't continue.
Yes, sir, definitely. And there was another question from Mr. Mohammed. Sir, are the segments are used for class 3, class 4, or are they reinforced?
Yeah, these are the reinforced segments, but usually when it is being designed, it is I mean the worst parameters are considered while designing itself from the GIR. So let's say you have grade 1, grade 2, grade 3. So the worst parameters are already being considered while designing the critical cases. So there is no as such differentiation when it comes to segmental lining. So it could happen cases where let's say you have a rock and you have a soil, so there might be a case where you may go for different segments with the different reinforcement, but ideally in different rock classes, because see, in NATM case, you are able to see the face 100%. So you can decide the primary lining based on that. But in segmental lining, every mining you are unable to see the face. It is only during the cutter head intervention you are able to see the face. So it is not wise to design for different classes. So they take the critical case and they design the segments uniformly.
Yes, sir. And there's Mr. Rahul Sharma wants to ask something. Rahul,
Hello,
sir?
Anshul.
Yeah, please. Hi, sir.
Uh, nice presentation. I just have one query. You said that you put the grouting in three layers, correct? One is 23 meter, again one 23 meter, and one is 6 to 8 meter. So with 6 to
Correct.
8 meter is okay, but how can you ensure the 23 meter of length your grouting is will be give a 100% efficacy for your going ahead works?
Sir, I mean, these are three different lines. If I just rephrase my sentence first. So what we did is we did these two lines in a staggered pattern, because if when we did the first line, we need to see what exactly the flows, inflows we are getting in the second line. So this was the first case. Second case is, like I said, this ground is hard. I mean, the only limitation, what I mean, the objective of the intent, what we want to do is to ensure that wherever these joints are there, we can consolidate with the use of grouting. You know, in a rocky condition, you cannot ensure the grout to the extent possible. It is only up to the level the joints are taking these grout. So what we did is the depth we decided based on the tunnel alignment. So because we don't know where exactly the fractured zone is sitting. So we did a, borehole up to 23 meter. Then we installed the TAM pipes, and then it is a bottom up grouting. So we started from the invert. Ideally, in the inverts, the flows were not as much as what we have, I mean, executed at a shallower levels. But it is a bottom up sequence. So every 0.5 meter, you are lifting the packer up and you are doing the grouting. So this ensured that the grouts are intakes are in place to consolidate the open joints.
Great.
I
Did
hope
you
it
do any
answers
test?
the.
Yes, yes. Did you do any testing after that grouting process to
Post
make sure?
grouting comparison you are making. again, sir, the point is, if you see here, we are not actually consolidating the whole ground. So ideally, we do pre and post thing. Let's say when we have a soil, we did either a replacement of soil or maybe consolidation of soil mass. Then it is wise enough to compare, because in this case, you are only consolidating the joints. So this joints is localized in nature. Even though you drill again, you will not be able to achieve that core.
Okay, range of pressure. This is the last question. Range of pressure which you
Uh,
use.
I remember we have in fact gone up to 8 to 10 bars at the
Okay,
bottommost point. Ideally,
sort of
for 20
consolidation
meter,
grouting.
yeah, 20 meter, if you see, theoretically 2 to 2.5 bar comes. So what we did is we incrementally increased, and then when there is a refusal happening, we had increased even up to 8 to 10. 8 bars, I think, was the maximum enough.
Okay, thank you. Thank you so much.